Okay, I wanted to talk about number 6 because it was kind of different. It was telling you to use the indirect method. And if you flip back to page 61, it talks about the indirect method. It said that the other method establishes the truth of a statement by proving every other hypothesis is incorrect. This is known as the indirect method of proof. So look at what it tells us to do. It says prove that the perpendicular bisector of the base of an isosceles triangle passes through the vertex of the triangle. Suggestion: use the indirect method. Note exercise 2.5, exercise 3, and informal statement on 7 on page 40. So let's go read those statements. Let's go look at those items. It says only one perpendicular line can be drawn at a point in the line. So in other words, if we've got an isosceles triangle, okay, we've got an isosceles triangle, triangle A, B, C. What they're asking us to do, it says, is prove that the perpendicular bisector of the base of an isosceles triangle passes through the vertex of the triangle. Okay? So, now by construction, we could have drawn that, where did my compass go? You know that we could have drawn the perpendicular bisector of this line by coming out here and drawing that on B, that on C, and then drawing a line between them. So I didn't do half bad. Okay, but we really should have used our compass in the first place. Okay, so what it's asking us to do, it says, is prove that it passes through the vertex. Well, informal statement 7 says there can only be one perpendicular bisector. So, in other words, I can't have another line that does this and is a perpendicular bisector, or another line that does this and is a perpendicular bisector. I can prove that all those other lines don't work. The other thing it directs me to is exercise 2.5, number 3. So if we flip back to that, it says, on page 58, it says prove that the line from the vertex, that's the top, there we go, the vertex of an isosceles triangle to the midpoint of the base bisects the vertex angle and is perpendicular to the base. Well, if we've already used this, then what we're trying to basically do is say, okay, is the converse true? Is it true now that we've proven this? Can we go backwards and do that? So, by indirect proof, what we want to say is, okay, so say we've got this point N. We've got NA. Let's label this P, and that way we end up with NP and NA. Well, let's suppose that NP does not pass through the vertex, but AN does pass through the vertex. So, if we look at this triangle over here on this side, get out my colored pencils. If we look at this triangle and this triangle, we know that they're congruent, okay, because of side, side, side. If this is a bisector, we know that this is equal to this. If they're an isosceles triangle, that means those angles are equal, which means this side is equal to this side. And of course, AN is equal to NA by identity. So by side, 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 we know that the green and the blue triangles are congruent, okay? Okay, so now we can name all of our corresponding parts. You know, this angle BAN is equal to NAC. This angle is equal to this angle. And I'm going to go ahead and write them as right angles, because how do we know those are right angles? Well, we said that let's draw AN as a perpendicular bisector. So by definition of a perpendicular bisector, these two are right angles. So therefore we cannot have both AN as a perpendicular bisector and NP, because informal statement says that only one line can be the perpendicular bisector of a line. So we've proven that by proving that NP couldn't be it, we've proven that AN would be a perpendicular bisector and go through the vertex. So you don't have to write a proof for this when you can simply draw yourself a picture and talk your way through it, making sure you use your little marks that show what's congruent and what's not to go through this.